So I'm Jalen,
I'm Kevin.
and our project for these past 5 weeks was mainly focused on processing simulation data, astrophysical data, and working on implementing that so that we could visualize it better. Okay. So it starts. There's kind of a hierarchy as to where all this data comes from. First, there's simulation code that lives in a software called Proteus, and it outputs a wider range of data that is hard for people to understand. But it contains a ton of information, and what we do is we kind of strain that information that makes it more understandable. So there's this other component called lava flow, which acts as kind of a strain to the simulation data, and and then it gets inputted to Whitey, and the Whitey project is a Python project will that we use to plot the domain, the space domain in in whatever way is useful to us. And then after we get those plots, we upload them. Our job was to upload them to Casanova in the PyNet. And there was a picture here that showed a handy diagram, but
Okay, so basically the diagram shows this hierarchy. Uh, if you could see the image on the left, you have Proteus branching off into YT and Lowflow, which goes to PyNet and eventually to the online database, which is Casanova, that the users can access.
okay. We work most closely with YT, and YT is a project that was worked on by astrophysics people throughout the world, grad students, professors, and it's open source. Anyone can work on it to improve it, to add functionality to it. And it's in the Python language, and it's used to visualize 3D data. So not just this astrophysical data, but also hydromagnetic data or anything like that. So the general gist of it is that it reads in the data set that is produced from Proteus, and then what you can do is you can specify what you want from YT, what you want YT to do with it. For example, I want to plot the temperature across this galaxy. I want to see how the density changes with respect to distance from a certain place. And this is what we get out of it.
Okay, so
All right. Okay. So this image was produced from real simulation code that was outputted, and we got to work with this big file. It was several gigabytes big, and how this 3D domain can be represented on a 2D image like this. You can either slice it like a 2D plane, or you can project it onto a surface. But we'll get to that later. You can see that we have plotted temperature here. So we use this pseudo color scale to represent that. And we have the X and Y axis. But you can specify, of course, whether you want it based on Y or Z or X or Z. So this plot is showing actually several things going on. We have an exploding star event, and over here, if you can see these waves, that depicts kind of Kelvin-Helmholtz instability, which is when you have two planes of water rubbing against each other. Eventually, it becomes unstable, and then it forms these clumps of waves. And I experimented with measuring that based on the width of the mix region when they mix together. He works with measuring how the momentum in the y direction changes and grows. Over here we have a galaxy, which we got from a sample data set from Whitey. And we chose to plot density, and you can specify this kind of scale that you want. This is logarithmic.
Now going to the technical aspect of this, you can't see it right now, but there are actually small squares, to put in layman's terms, and across this projection, and basically, these squares are what make up this projection. As the squares get smaller, it's basically like
A mesh.
Yeah, it's a mesh, and you can think of it sort of as an integral, a Riemann sum, like if you remember from calculus. The the rectangles get more and more narrow, and so this is the same idea with this. You have smaller and smaller squares, which help to make the projection more fluid, and the size of these squares varies across this projection depending on where it is based on this parameter.
And here's some more pictures. The left one is the right one zoomed in. So if you want more precision, then you can tell YT to zoom in on a specific area. And to the right is something called an average radio profile, which Kevin worked to it. So how it works is instead of plotting it in a two-dimensional fashion, you specify a center, and whatever the data is plotted based on its distance, its radius from that center. So these are the three main types that we have so far. We are going to add more. And to the right, you'll see YT outputting a bunch of information while it's processing all this data. You see YT and then info, and then July 13th, 11:25, which is when we were making this PowerPoint. And you see all this stuff that it's doing. So the first type of plot we have is a slice plot, which is you have this domain, this 3D domain, and you say, I want to slice it at this specific spot. You want a specific plane, and it's a matter of precision, right? So if you want the slice to be over here versus over there, you can see, versus a projection plot, which is the entire thing. How I like to think of it. It gets smushed. The entire thing gets smushed into a pancake, and then you get to see everything.
Also, we had intended to plot column density, which is basically you take let's say you have a circle, you take a slice of that circle, you have you have density from the center to the edge of the circle, and then you sum the densities, and you basically have the density all pushed all the way to the circumference of the circle. But then we weren't able to do that because it is no longer there is no longer pre-written code for that in YT, so we had to manually do that, which didn't work for us.
Okay. So this is pretty much our role, the two of us, in this whole project. So we're implementing a driver inside the PyNet, so there's the Casanova archive, and we are taking the simulation data, we're producing plots with Whitey, and then what we're going to do is we're going to allow that to end up on the archive. So how it works is the user will specify, I want a projection plot of X, Y, Z or something, and depending on what input we get, the driver will determine what to produce as an image, and then it also asks for the variable that you want the variable in question, such as temperature and density, and the output file name. And it can also, because of the flexibility that we have with Python, which has helped us, we can also process a list of data sets to process at once. And Casanova, that if you're wondering about the name, that stands for Computational Astrophysics Simulation Archive, and the Nova makes it sound more Italian. And eventually, Casanova is going to be available to the public for all to see our results. For the future, what we're doing now is we're going to add more functionality to our driver, not just the 3 plots that we have, but we're also working on fractal dimensions, which is something that a previous YSP student has implemented in the past in C++. So we're working on integrating that into our driver. Plus a lot more, but we'll see. Oh, all right, that's it.
Thank you very much. Questions?
So what was your experience in Python going into this project? You had past experience with it, or were you new to learning the Python language?
Well, we were both pretty unfamiliar with this language, but alongside this, we were also taking a Python course. It was part of the program, so that helped us with the syntax, learning the syntax, and how to think of the code.
I'd say that having to switch to Python at the beginning of this only helped us in that it was more flexible and it was more suited to the scripts that we wanted to implement.